Hi everybody, this is Matt Morgan. In this lesson we're going to talk about hydrolysis from Wiley section 13-7. We'll define hydrolysis, talk about what it is, how hydrolysis makes acidic salts and basic salts, and which ions will react. Finally, we'll work an example from the Wiley homework. So when an ionic compound dissolves, the ions separate and they're surrounded by water molecules. For sodium chloride, this particular reaction is written, we have solid NaCl goes to aqueous sodium ions and aqueous chloride ions. If we look at this picture, we'll start with the sodium chloride crystals, the ions in an orderly array. When water molecules come in, they break the ions off, and the ions are still in the water, but separated. They're surrounded by water molecules. Here's an animation that shows that. Once the ions are free in solution, some of them can react with the surrounding water molecules. In order to attract these ions, the water itself breaks up into H+ and OH- ions. There's our equilibrium. And that's where we get the name hydrolysis. Water splitting, hydro and lysis. If you've taken a biology course, you might remember lysis as the splitting of a cell. This is the splitting of a water molecule by the presence of ions and the subsequent reaction. So negative ions will react with the H+ ion from water. If we have a cyanide ion, we have both H+ and OH-. OH- is not going to react. Those like charges will repel each other. The H+, however, will be attracted to the cyanide ion, and they will even combine into an HCN molecule, also leaving OH-. Positive ions will react with the OH-. Here's an ammonium ion. The H+ has a like charge. Those will repel the H+ and the ammonium. The hydroxide, however, is attracted, and we will get ammonium hydroxide with a leftover H+ ion. So here's where we get acidic and basic salts. When the positive ions react with the OH-, we have an H+ remaining and we have a slightly acidic solution. With our ammonium example, we have ammonium plus water giving us ammonium hydroxide and H+. Now in Wiley we won't see it written this way. Wiley, rather than write H+, they like to write the H3O+, the hydronium. So the hydrolysis of ammonium will take place with two water molecules giving us the ammonium hydroxide and the H3O+. Just remember, for all our purposes, H+ and H3O+ mean the same thing because water is our solvent. And in other textbooks you may see H+ written. When the negative ions react, an OH- remains, and that gives us our basic solution. If we have the chlorite ion plus water, we get HClO2 and a remaining OH- ion. That gives us a slightly basic solution. So which ions react? Does every positive and negative ion react with water? Okay, well here's where hydrolysis gets a little tricky. The truth is, not all ions react with water. Okay, and that makes this hydrolysis a little bit difficult to understand. But fortunately, we can tell if an ion will react with water or not. It requires us remembering our strong acids and strong bases. The conjugates of strong acids and bases will not hydrolyze. You want to write that down and think of that. The conjugates of strong acids and bases will not react with water. So you remember your strong acids, right? Absolutely. But let's go over them again just in case it's been a while. Strong acids are hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric. Those are our 6 strong acids. The conjugates of these strong acids are the ones that will not react with water. So we get chloride ion, bromide ion, iodide ion, nitrate, perchlorate, and the hydrogen sulfate. These ions are spectators. If you see a chloride ion or a bromide ion or a nitrate, they will not undergo hydrolysis. Okay, other negative ions, like the cyanide that we saw, like the chlorite that we saw, those will react. So group 1 and group 2 cations will also not react with water. They're considered the conjugates of strong bases. Just go down group 1 and some of group 2. Okay, solubility considerations keep magnesium and calcium from being on this list. And most of the time you'll just see the group 1 cations listed. They will not react with water. They're spectator ions. So let's look at a Wiley problem. Let's apply this knowledge that we just went over. This is 13-086, the aqueous sodium fluoride solutions. It tells you they're weakly basic. And sodium chloride is neutral. So let's write the net equation that illustrates why sodium fluoride is slightly basic. Double arrow and do not include states. The salt we are given is sodium fluoride, and that breaks it up into Na plus and F minus ions. We first need to determine which ions, if any, will react with water. Na plus does nothing. It is a classic spectator ion. It is a group 1 cation, so it's not going to react with water. But the F minus, is that one of the conjugates of a strong acid? It is not. So our F minus will react with water. And since it's negatively charged, it will react with the H plus, giving our reaction F minus plus water gives us HF plus OH minus. That shows us that the fluoride ion is slightly basic. Okay, we'll look at that answer. We'll put it in. And check. Ah, it is correct. That's what we want. F minus plus water, double-headed arrow, HF plus OH minus. Now to the second part of the questions. Why aren't sodium chloride solutions basic? Let's look at all of those answers and determine which ones are correct and which ones are not. Okay, NaCl remains in the molecular form. Okay, that's not correct. It's an ionic compound and it's a strong electrolyte. It definitely breaks apart both into sodium and chloride ions. So that's not a good answer. HCl remains in molecular form with strong dipole-dipole interaction. It's a precipitate. That's not correct. HCl is a strong acid. It completely dissociates. The Cl minus is also a spectator ion. Okay, hydrolysis of the Cl minus does not occur. HCl is a strong acid, does not exist in molecular form. Ooh, that statement looks really good. We're going to hang on to that for a while. Then finally, NaCl is a strong acid and therefore a very weak base. What? NaCl is a salt. It's not a strong acid. So that answer's definitely out of there. I think by process of elimination, this is our correct answer. Let's check it out. Okay, choose hydrolysis of the chloride ion. Does not occur. Boom, that is our answer. So, we discussed hydrolysis, how the reactions proceeded, which ions will react, and which ions won't. And we went through an example from Wiley discussing acidic and basic salts. If you have any questions about these concepts or any others in the course, you know who to. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.